All right. Good afternoon, everyone. We may still have a few people coming in, but I want to welcome everyone to this fall's celebration of our physics and astronomy capstone students, as well as we have a few of our students who participated in either internships or REUs, research experiences for undergrads, that will be telling you about their experience after our capstone students. We had originally planned on starting with our space physics student, Kate Walker, but she is unfortunately unable to present today. So instead, you get to start off with Emily Strawn. Emily is a senior in astronomy. She's graduating this term. She's been doing research with myself. And today, she will be giving you a talk about the orbital analysis of the universe's best binary, Ada Carina.
Thank you for that amazing introduction. Like Dr. Richardson said, my name is Emily Strawn. I'm a senior here at Embry-Riddle, and I've done my senior thesis on an orbital analysis of Ada Carina. There we go. So first, just a little bit of background information about Ada Carina. Ada Carina itself is a binary system embedded within the Carina Nebula. That's just a way of saying it is two stars orbiting each other inside of a cloud of dust and gas. And then these two stars do get particularly close at Periastron. Periastron is a term you'll hear me using throughout the presentation. It just means the closest point of the two stars' orbits. All right, so to get a bit more into it, sorry, let me double check exactly which slide I'm on here. There we go. For our orbital analysis, we looked at the radial velocity of the primary and secondary star. I will go ahead and talk a bit more about the secondary star later, but to start us off with the primary star, we looked at the hydrogen emissions, which is what these plots up on the screen now are representing. Each of these 9 plots are a different snapshot of the hydrogen emissions. That nice little black curve that you see going through the middle of the plot with that nice bump in the middle, that is the hydrogen emissions with the height corresponding to the abundance of hydrogen. So if you look also at the width of that bump, that is caused by the broadening from the movement of the star. So we are looking at that width to determine the radial velocity. We track it from the left hand to the right hand side, and that is what all of those points in the middle of the plot are representing, that nice little squiggle. It's just showing the distance from the points to the left-hand side to the right-hand side. So by looking at many of these plots and comparing all these little squiggles together, we are able to determine this middle region. Ooh, I do have a laser pointer I can point out. This middle region between those two dashed lines as the most appropriate region to represent radial velocity. You'll notice that above it and below it, it does kind of squiggle off in 2 different directions. That's just due to some other things going on. But we isolate those middle points. We average them all together to get 1 point per day. And then we are able to plot them all together. So this plot on the right-hand side of the screen up here is showing the velocity of the star. So it's showing how they speed up as they get close together and then slow down as it moves further apart. And then we are actually able to go through and compare this to a previous analysis done of Ada Carina by Grant et al. That is what these plots, on this hand side of the screen, there we go, are representing. This top one is the same type of velocity plot that we made over here. And so by comparing them, we are able to see that the results were relatively consistent all around. The actual biggest difference between our analysis and theirs is the methods used to find velocity. So let me actually go ahead and back up here just a step. You'll notice that I went ahead and I found the velocity by fitting 2 lines. They have these gray little lines on either side of that hydrogen emission, whereas what this other analysis did was they used a multi-Gaussian fit. That's what this plot is down here to find the velocity instead. The main reason we chose to go the other route of doing 2 polynomial fits to either side of the emissions is simply because it was a simpler procedure to be done. It was easier in the end to be able to do. And this Gaussian fits got a bit too complicated for me to handle, but also means that in the end, hopefully people will be able to go through what we've done, review it over, and be able to have a good understanding of how we got to where we were, which I'm sure you're all familiar is a very strong foundation within research. All right, switching gears a little bit from the primary to the secondary star, as I promised earlier. A quick thing to note about the secondary star is that we know very little about the secondary star. So in order to look at the radial velocity, we actually use the helium-2 emissions, which is what this plot over here is. A thing to realize of this plot, if you haven't noticed already, is that it is exceptionally weak. There's actually only that about there we go, that 0.01 difference, that 0.1 strength. And so we had to do a few things to make it a bit easier to observe. This includes avoiding observations near Periastron, so avoiding when the stars are close together, because as they get close, there's just a bit too much going on in order to reliably observe this emission. The other thing we did is we combined data from multiple different days all together, because of course, more data means a better fit in the end. So then we are able to go through and get this nice little Gaussian squiggle fit that you see here. We used a Gaussian fit simply because we are able to do it using just one Gaussian. And out of that, we are able to directly get a singular radial velocity corresponding with this emission. That is what this nice vertical line here is representing. So once again, we got that singular data point for every day, that singular velocity point, and we are able to plot them all together. That is what this plot here is. Same thing as before, just a velocity plot. But of course, the kind of obvious difference is there's significant fewer data points on this plot altogether. This plot alone is not enough to be able to confidently say that what we are observing here is the velocity of the secondary star. Now, what is really exciting about this plot is simply the fact that we are able to get this point and get these results and create this plot. Because honestly, in the beginning, we were not completely confident that we were going to be able to get to this point. But now knowing that we are able to actually get these results out of the helium-2 emissions, it does mean that it's a great motivator to be able to go back in the future, take more data, which my absolutely amazing mentor, Dr. Richardson, is already working on a bit. And hopefully in the future, someone will be able to come through and do a further analysis and get even better results out of this, which is honestly my favorite part of this entire research project, is that I feel like it sums up the experience of being a researcher. It is the point that while I might not go through and do the further analysis myself, I will be able to hopefully someday see more amazing information and knowledge learned about Ada Carina and be able to know that I had a part in the early foundations of it. Of course, I can't get away without talking about the last little bit of amazing things I've done on this project, which is the fact that I am currently working on finishing up a paper, which we hopefully will have submitted for publishing by the time I graduate, which would be so amazing just to have that out there. And I can't have asked for a better way to wrap up my senior year. Thank you.
Before Dr. Grutterson, are there any students with questions? All right.
Yes, indeed. Students go first. But we get to go in the end, which is always the most fun part. Emily, could you go back? Thank you, first of all, for a really nice talk. It was very clear. Could you go back to the slide where you had the primary velocity?
This one?
Yeah. So the spread of your data, particularly the yellow points on the right, it's not random and therefore indicates that that is an unmodeled deviation. Do you have anything to say about that?
I'm sure that my absolutely amazing mentor would be able to sum it up a bit better than me. Honestly, my expertise kind of ends with the program I used to make the fit.
Flattery does not get you extra credit in your capstone. There's likely some other things going on that we are not modeling. We're just going for basic kinematics of an orbit. There's probably colliding wind effects within the profile that, honestly, my colleagues and I are still baffled that we can do this. So that this is, in my opinion, I think this recent paper from last year and Emily's work this year, this is the first time we've really had any kind of kinematics of the binary. And the major and amazing thing that Emily has done is a potential detection of the secondary, which has eluded observers since it was first inferred in the 1990s. And no one has really detected this directly. So kudos to Emily for doing a very, very hard analysis. And I'm sure her paper will garner a lot of interest within the massive star community. And I look forward to publishing that. But before that, any other questions today? Okay. Well, thank you again, Emily. The other capstone student we have talking today is Connor. So Connor, why don't you come up and set up the thing? And Connor has also been working with me since about the same time. And Connor is also going to talk to you about a very intriguing object that I like that's also named Ada Carina. But he is focusing on a very different aspect of the physics in these observations. So, Connor, Mr. Pickett, will you take it away, please?
Well, thank you for that wonderful introduction, Dr. Richardson. As he said, I am Connor Pickett. I am a senior in astronomy, and this is my thesis that is about the changing nature of the ejecta around Ada Carina. So a little bit of an overview. I'm going to bring you through the background of what Ada Carina is. I know Emily spoke about it, so I'll go through that a little more quickly. I will be telling you about the goals and methods I use to measure the data that I received from Ada Carina. I will talk about my analysis, which then led to the discoveries that I've made, and then the final results that we will be discussing in an upcoming publication coming out hopefully much the same time that Emily's is. All right, so a history of Ada Carina. It is a massive binary star in the Carina Nebula, with in the two stars in the system have a binary period of about 5.54 years, which means that they do a full orbit of each other in about 5.5 years. And the closest of these orbits, as Emily stated, is Periastron, where the stars are closest to one another, and they have pretty interesting data at that point. Ada Carina is actually very weird as well because it erupted twice in the 19th century, with the first being the Great Eruption, and the second being the Second Eruption, you know, not the most exciting name after the Great Eruption, nothing can beat that. But that created the homunculus nebula that we see around the star itself. And that's where a lot of data that I worked on actually came from. Some of the goals and methods that I used to perform this analysis. So I used spectral analysis that I looked at the spectrum of Ada Carina, and I looked at absorption lines within Ada Carina itself. So if you look down here, this is a continuum from a spectrum, and right here is actually sodium absorption, and that occurs at around 5,890 angstroms to about 5,900 angstroms. I actually looked at a wider range just to get a better view of what that region was actually about. So that is why my range of wavelength is a little bit bigger. It gave me a better view of what was going on in Ada Carina. And with my methodology using this spectral analysis, it was a lot of coding. I was completely new to Python when I started, and that was a huge hurdle that I had to get over when I started this project, but now I love Python and I love Jupyter Notebook, and that's what I've used mainly for this project. It's been a journey, but I've enjoyed it very much. So my analysis, sodium D, so as I had said, that spectrum that I showed you was the absorption lines of sodium D. And Ada Carina has much of a similar absorption pattern. Sodium D is actually a doublet line, meaning that it's not one single absorption. Due to the Zeeman effect, which is induced by magnetic fields, there is actually a doublet line where it splits, and that gives me two very deep absorptions to look at. So over here on the right side, you can see these two main absorptions. There are certain absorptions kind of in the intermediate sections here, and during my analysis, a lot of those absorptions in the blue are actually ones that I did not want. So what I had to do with this spectrum is actually do a telluric correction, with telluric meaning water lines from the atmosphere. So because these are ground-based observations, I actually had to go through and remove any sort of noise from Earth's atmosphere. So in my analysis, this orange line right here is actually the clean data. So I had to go through each file, which was about 700 files, gross, and I had to go through and clean each one and make sure that it was actually well enough and clean enough to analyze properly without getting any extra data that I didn't want. And then after that was done in my later steps, I went through and I analyzed the equivalent widths or the strength of each absorption line that I aimed to analyze from the beginning. So there are two features. Well, there used to be one feature, but it is moving at negative 144 kilometers per second, as well as negative 168 kilometers per second. So in this plot, you can see this very deep absorption that is separate from the two main absorption lines. And that is the absorption that has been analyzed by a few other scientists, but it wasn't too well understood, but it is moving, which gives us a better understanding of what is going on. So it was at 144 kilometers per second, which you see here, it was actually strongest in 2010 to 2014. But by 2015, it was getting very weak, and it had pretty much dissipated by the 2018 data. That was not a Periastron, I misspoke. But by the time that I got data from 2020 during that Periastron event, it actually seemed as though the 144 feature had moved to 168. And that was quite interesting because that means that something else was happening in Ada Carina than just material absorption. And it had continuous growth, and we expect it to keep growing, but it was something that we had to look at during this analysis. And here we can see the equivalent widths, which are obviously changing, especially with 144. Each one of those increases is from a Periastron event, where the equivalent width gets much stronger. And then over here for 168, it's not a full plot because it's a relatively new feature that we're trying to look at, and it's weak right now. But you can definitely see a trend of it going up, and then we expect it to have a similar pattern as 144 once it becomes stronger and in later events. There was a new discovery of an absorption at plus 88 kilometers per second, or as I like to call them, the picket lines. This was a feature that had remained after telluric removal. So right over here on the far right, you can see that there was a feature there that wasn't removed when I removed any water lines. And that was something that was a little weird for us to look at because it wasn't something that was expected. It was relatively weak, and it was bizarre because, again, it had never before been seen. It was at a positive velocity, and we expect usually sodium absorption to occur at velocities that are much weaker than 88 kilometers per second. Usually the strongest was at 10 kilometers per second in the positive region, but this one was much higher, which confused us. But that's why we do research, to understand what we are confused about. Here we can see the equivalent width of the 88 line. And you can see it over here in this GIF. It is not growing too much. This spike right here is due to the relative flux of Ada Carina. So as that flux increases, the continuum also increases, and the depth of the line seems to get bigger. It's not quite getting larger. It's just a kind of a weird occurrence that happens when the continuum increases. So that's what this variability is. It's not varying as much as this plot leads some to believe. Here is a plot that shows, so there is actually consistency of 88. You can see that this data down here is a little weaker due to a low signal to noise. But as we get better data and better resolution of the data, you're able to see that the 88 feature remains relatively consistent. Over here, you can see that the 144 feature, which started around 144, is starting to move towards 168, but is dissipating. And we start to see signs of 168 over on this side, though it is very weak right now. And then to further analyze this absorption, we wanted to understand where it was coming from. So we looked at stars in the relative neighborhood of Ada Carina, and that gave us an idea that this absorption was not coming from something intrinsic to Ada Carina, but rather more of an interstellar medium cloud of gas and dust between our line of sight and the star itself, or the system. Whoops. There we go. So if you can see over here on the right side, there are absorptions near 88 kilometers per second. It might not always appear at that velocity, but that also tells us that this cloud of dust is not uniform and it is not a continuous symmetric sphere of material. It is varying in its strength and velocity, but it is relatively clear to see that this absorption does appear at other regions. Up at top is Ada Carina, and comparatively to these stars, you can see features that are caused by this gas and dust. And then the results from all of this analysis, to begin with the 144 and 168 kilometer per second absorption, we do see that because of this dissipating strength, we believe that the ionization of the inner walls of that nebula around Ada Carina is causing it to dissipate. So the more gas it gets ionized, the more it disappears, and the next wall outside of that starts to become ionized as well, and that gives the absorption lines that we see. So this one is lovingly known as the Connor clump that is dissipating. So that is giving us an idea of what is dissipating and at what point this wall of the homunculus nebula is going away. And as I said, that causes the weakening of the strength of the lines. And then with the 88 kilometers per second absorption, we do see that it is not intrinsic to Ada Carina, meaning that it is not a part of the walls around Ada Carina. It is more likely a gas and dust clump out here that is between our line of sight and Ada Carina itself. And that is something that we're still trying to understand. It's difficult to understand the motion of it right now, especially at such a high velocity, but it is something that will be actively researched, probably not by me at this time as I'm graduating, but it is something that I think is very interesting that nobody's ever really picked up on before. It's something that will affect our analysis of other stars in the system, not just Ada Carina. And that gives us the picket lines, as I noted before, 88 kilometers per second. So that's my research. Thank you.
Thank you very much, Connor. Are there any questions for Connor today? Guess that means you did a good job. Thank you again. Now, as part of our fall series of talks, and as a way to hopefully inspire some of our students to go and try some of these things, we have invited today 3 of our students that have participated in internships or REUs, research experience for undergrads, to give a brief talk about what they worked on last summer. These are wonderful opportunities for you guys as students. They're a way to get paid to do some fun physics-related work over the summer. So I do encourage you guys to apply for these. So who wants to go first? Okay, Jennifer, you're up. All right, so first up we have Jennifer, and she's going to tell you, I believe she has an REU that she talked about, or that she's talking about. I'll let her bring that up.
Great crowd. Thank you.
There we go. All right. So this is Jennifer James, and you did an REU, and you'll tell us where that was and everything. And then if you have any questions, feel free to ask her at the end. Thank you.
Hi, everyone. As he said, my name is Jennifer James. I'm a current space physics senior here at Embry-Riddle. I'll be graduating in spring. This was my research experience for undergrads with Indiana State University at Bloomington. Unfortunately, I did not get to physically be there, but I did get paid a handsome amount to do some virtual research. It was pretty sick. So my mentor was Dr. Walter Patus, and he is a wonderful faculty. He's brand new at Indiana. And together we did the stability of pulse shape analysis in Neutrinolist double beta decay. Oh yeah, there's a remote. Okay, so unfortunately I did not get to visit Lead, South Dakota to get into this 4,000 feet deep hole in the ground where we studied our research and got our data. This is SURF, Stanford Underground Research Facility. And basically, we are, where is it? Oh. Anyways, we're in this corner right here. And so further on, moving on. This is the detectors that we use. So we use germanium-76 detectors. And basically, we got to make a bunch of arrays, about 58 detectors, and we get a bunch of data. And we are looking for data from these point contact detectors. We are specifically looking for the Neutrinolist double beta decay. So basically, beta decays happen in the weak interactions. And we normally get this over here on the your left, my right. And what we're looking for is a very rare decay where the kinematic or the nucleon is kinematically not favorable, and we are produced 2 electrons who also produce 2 antineutrinos. And if we are assuming that a neutrino is a Majorana particle, it must eliminate itself and therefore has mass in order to conserve energy. And so in the experiment itself, we're looking for this monoenergetic peak. And what we get from double beta decay is this big blue line. So great. But what we're looking for is very tiny and very small. It is very rare. And so we, at the Majorana collaboration, have yet to find it. But we are moving on to the Legend 200 and 1000, which I will talk about in a minute. And so specifically, we're looking for a single side event versus a double side event or multi-side event. We call them the single event peak or the multi-escape peak. And basically, this interaction between the electron and it releases a photon, or sorry, a neutrino. Okay. So graphically, this is what it looks like. So the single side event on top is what we are looking for. This is very clean. What we don't want is for this small bump to appear in our data. And so basically we get a parameter called A versus E. And A versus E is basically a calibration of thallium-208. And it is an energy calibration. And it tells us that we can eliminate all the multi-side events and be stuck with all these single-side events. And so the one I'm looking at today is the little yellow line in that red box. 1302 is the channel. And it is produced at 1592 keV. And we are presented with this double escape peak, or AKA the single-side event. And what I found is this continuum, of course, across this data at that channel, at that energy level. And presently, we are given these 3 DEP ranges. So basically, each DEP range is 1 day of data. I took 2 weeks of data and I analyzed it, but for the purposes of presentations, I summed it down to 3 because it all looked the same. We get a range that travels, which basically tells us that our detectors are not stable. So kind of bad news, but it was also in a week where we turned off the detectors every day instead of leaving them on. So that was our inconsistency in our data that 2 weeks. And then we are left with a peak position that I placed in 2 places. I did the 1302 channel and another channel. And it just tells us that that's what the peak looks like in that section. Nothing too crazy about it. But that red line right there tells you that it is inconsistent. It is not very straight. It's not very stable at all. So the future. We have Legend 200 and Legend 1000. Basically, we're going to have a lot more germanium, a lot more detectors, and I maybe will work on it. I'm hoping to work at the right lab and work with QR and Cupid for Neutrinolist double beta decay. Here's 1000. I'll give you a second to read those points. But the main highlight is that we're going to, instead of a copper chamber, we're going to cryogenic cooling. That's the big switch. And so I hope you enjoyed my talk. If you have any questions about Indiana or any opportunities in the future, or of course Neutrinolist double beta decay, I am here to answer your questions.
Thank you, Jennifer. Are there any questions today? Yes, Megan.
Kind of what is like the benefit of switching to the cryogenic method?
Okay, good question. So we use copper to avoid thorium and uranium contaminations, but the argon cryogenic cooling will produce better results in terms of getting more events, such as the Neutrinolist double beta decay. If you don't have a cooled system, you're not going to receive that weak decay as much as you would if it was cool.
So the other thing that you can get from that is a really good signal-to-noise ratio when you cryogenically cool the germanium detectors. So, so when you're looking for that formation at the end of that spectrum that you were talking about at the beginning, you can really study that in great detail. So that spectrum, could you go back to the beginning of that,
Yes.
where you showed that initial spectrum? And so you're looking at the high end of the spectrum. I assume you're looking at the energies of the 2 electrons that are coming out. Is that what you're plotting there on the...
This spectrum?
No, keep going. Yeah, it's almost back to the beginning. There.
Whoop.
Yeah, so you got 2 electrons coming out in both cases. So this spectrum, you're measuring the energies of those electrons, those
Yes.
2 betas coming out? Okay. And so what you're looking for, and then go back to the previous picture, is, no, before that.
Oh, I'm going the wrong way,
where
sorry.
where you had the little Feynman diagrams.
Yes. There we go.
So in the case of the Majorana neutrino on the right, you expect a different contribution to that spectrum compared to having free neutrinos out there. So you're looking for a bump out at the very tail of that spectrum or something.
Yeah.
Okay. And single site and double site, I assume you're trying to differentiate between the possibility of having a simultaneous beta decay from 2 different locations in the detector, and you're trying to make sure they're coming from the same nucleus and
Correct.
not 2 different nuclei.
Correct.
Yeah, okay, good.
Thank you.
All right, one last question from Parker, and then Jeremy, you're up next.
Thank you for the talk, first off. I just kind of want to ask like a question for everyone. Like, what was your application process for this REU?
Okay. So the application was due in February of 2020 or 2021, and I started the application in December, I want to say. Basically, there was no application fees, and it was all pretty straightforward. It was a bit bumpy, so basically what happened was they lost my application, and then they called me and said, hey, this guy just left. Would you like to have our position? And I said, yes, please. So I got lucky, very lucky, but they did tell me, and I will brag, I was up there on the list. So it was not hard at all. It's very doable, and I honestly will say it's easier than grad school and undergraduate school applications.
Well, thank you again, Jennifer. And Jeremy, you're up.
All right, good afternoon, everyone. For those of you who don't know me, my name is Jeremy Gordon. I am a senior in the space physics program as well. I unfortunately do not have any fun PowerPoints to share. That's partly because I actually am going to be speaking on behalf of my internship, and that was with Raytheon Missiles and Defense. And as you could imagine, I'm working with a lot of classified and proprietary information. So it kind of makes it hard when I need to make a PowerPoint that I can't really show a whole lot of things to a large crowd. But I will summarize. I've actually had 2 internships with them. The first one was in the summer of 2020, and that's right as COVID started to hit. But I was thankfully still able to go down to Tucson, and my internship was very hands-on. I was assisting in the environmental test program, which is not actually testing the missiles in the testing our missiles on the environment. It's actually testing our missiles in the environments which they'll see service in. So I was responsible for setting up large-scale tests on different missiles or missile components and pushing them to the limit of what they would see out in real-world use. As well as beyond that to know the lifetime of different products that Raytheon has. But by the end of it, I kind of realized that that wasn't really the area where I wanted to pursue my future. It wasn't very physics-based. In fact, I would say for the work that I did, I probably had to use 0 physics for it. But I was granted the opportunity to come back this last summer, and I was working with the electro-optical engineering department. And there was actually 2 colleagues that I got to work with who both have their PhD in physics and are working on physics simulations for the electro-optical sensors. My goal was to work with a new sensor that is going to be put into one of Raytheon's new products. And the biggest push for it was changing the input data from analog to digital. Essentially all that means is instead of 16 bits coming in, 32 bits of data would come in, which allows us to get a higher dynamic range, allowing us to get more colors per se. It was a infrared optical detector, so it's not actual colors, but the greater dynamic range allows us to pick out greater details when discriminating targets. I got the very fun task of combing through C++ code to determine where in the code the changes would need to be made to switch to a digital input on their environment, or they're testing it in a real-world environment. I was responsible for additionally determining what requirements needed to go into the simulated real world, because as you can imagine, as we're feeding the seeker more data, it takes more time for it to process it, and when you're working on something that's possibly going to intercept another object, you need it to interface very quickly. So I was also responsible for determining what other subsystems, such as like lens flaring, just glaring, any sort of blurring from the motion, what needed to be included in our physics simulations so that when we tested it before it's tested in flight, we know what to expect from it. And from that, that's actually, I was offered a position to return back with them for this next summer as a full-time employee, and I would be continuing working with the electro-optical subsystems group, creating and adding to their physics simulations of their seeker systems. But with that, does anyone have any questions for me?
Thank you very much. Let's give him a round of applause, and then we'll do questions. All right, first up is Dr. Grederson again.
Hey, sounds like real work. This is like, and exciting too. My question though is, what is the electro-optic part of this?
So the electro-optical part is kind of a combination of really all of the seeker optics in general. The electro-optics is the essentially CCDs that are capturing the incoming photons or charged particles. And really, that's just the name. I don't.
Yeah, I guess what I'm really getting at is, do you know if there was any like active filtering through electro-optic components? That's a kind of an advanced technique.
Yes, I know that there is. That wasn't something that I got to personally work on, but I was in a couple meetings where my colleagues were going over some of their proposed filters for the visible and the infrared seeker.
Any other questions for Jeremy today? All right. Last but certainly not least is Alexis Lane. She did thank you, Jeremy. And then Alexis had a pretty awesome internship at the Naval Research Lab outside of DC this last summer. And she'll be telling you all about stuff with detectors that she was trying to characterize.
Sorry, stuff didn't carry over so well with the PowerPoint. I wasn't expecting it to open in this app, so I don't know how to present this in a way if anybody else does. That is something I can do. Yeah, I can't read. I'm sorry, I'm blind. I'm so sorry. Thank you. I'm not used to this. I'm used to my Google presentation docs, so. All right, sorry. Okay, so I'm here to talk to you guys about low noise silicon photodiode detectors. And I did an internship at the Naval Research Lab in Washington, D.C., and I worked under Dr. Cleo Sleater. So I did a bunch of projects with them, testing X-ray detectors, gamma ray detectors, testing ASICs for some other projects, but I mostly focused on these X-ray detectors. So to give you a bit of background on X-rays and how to detect them, X-rays are a higher energy, lower wavelength type of radiation. And they're emitted by galaxies, stars, supernova remnants, and many other things. Rather than measuring them in wavelength, we often measure them in kiloelectron volts, which range from 0.12 to 120 kilovolts, electron volts about. And we cannot detect them from the ground because they're absorbed by Earth's atmosphere. So we use balloons, rocket sondes, and satellites. And to collect them, we use capillary optics, which direct the X-rays toward the detector. And there are three types: mono, poly, and tapered. So the type of detector that's often used, at least for the stuff that we're doing, are silicon drift detectors. And they measure the energy of incoming photons by the amount of ionization that they produce within the detector. And then these ionizations create electron hole pairs, which a bias voltage directs towards an anode. And they have an active area up to tens of millimeters squared, which will be important in a moment. So what my group is proposing is a telescope that has an array of capillary optics, each with discrete detectors, with a focal length of about 10 centimeters. Yeah. And currently, the silicon drift detectors are the state-of-the-art solution to this, but we have some problems with them, such as their active area is a little too large for what we want, and the majority of this will collect just background information, not actually what we're trying to look at. And they also require quite a bit of cooling power with the amount that we need for this telescope. So that leads us to our detector. And so here's the CAD design of the detector. It has a central pixel, which is just used as the generic active area to collect stuff. And then inner and outer rings, which can be used either for anti-coincidence background rejection, or we can increase the collection area. Just do that through different wire bonding arrangements. And then there's an inner guard ring that just reduces the leakage current, and outer guard rings, which just smooth out the potential difference across the detector. So about the setup, compared to the silicon drift detectors, these are smaller, lighter, lower powered, more sensitive, and they also have a flexible design, as we showed with the inner rings. These already have the built-in anti-coincidence background rejection, and the second iteration of these has introduced a window, which you can see in the picture. This little dip right here, which allows us to have a higher sensitivity to lower energy X-rays. And so this is paired with an ASIC to read out all the data, which you can see here, just the general setup of it all. And just to give you a size of the scale, give you a sense of the scale we're working with, here's our whole detector board compared to a penny. And so right in the middle of all of that is our actual detector that I just showed you, which is blown up over here. So it's pretty small. So what I did this summer was I just tested these detectors under certain conditions with an americium 241 source. We did cold chamber testing. And the whole goal of these was to not have as much cooling power required for these detectors. So so we tested it all the way down to minus 60 degrees Celsius, and we found that there's really no change. So that's super good news for when we have to put hundreds of them together. We tested different bias voltages just to see what would be the most convenient and lowest power that we could use. And we also tried to see if we could increase the resolution by testing it with a digital shaper. But everything seems to be pretty good just the way it is. So that's good news for us. We have a pretty good detector. And then we were going to test the flexibility of the design, but we had trouble with the wire bonder before I left. So that's kind of coming up in the future. And moving forward, we're going to start testing it with the capillary optics and continue testing with alternate configurations. And hopefully in the future, this will become an alternative to the silicon drift detectors and used in X-ray satellite detection stuff. So here's all the stuff I used, and that's it. If you guys have any questions.
Thank you, Alexis. Are there any questions for her today?
Hi, Alexis. Yeah, you were saying that the silicon detector is the sensitive region is the pixel area, the round part and the central part. And you were talking about testing it with americium 241, which is an alpha emitter. So you got ionizing radiation going in there and making the ions and the electrons. But you talked about at the beginning of the talk about using it as a gamma ray detector. Did you test it with gamma rays?
We're using it as an X-ray detector. I worked with other gamma ray detectors.
Or X-rays. Did you test it with X-rays?
Yeah, we had I might have lied about the americium number, but I think it's 241. I'm pretty sure it's 241. We just had a source on top that, honestly, I don't know much about it.
Okay.
But I know we tested it with americium and iron.
Okay, iron 55 or something like that.
I believe so.
That's a gamma ray or a soft or a hard X-ray. Yeah. Okay. Okay. Good.
Sorry.
So Eric from the Planetarium here in the back. I've been monitoring the online chat, and I just wanted to send out something the Vice Chancellor just submitted. Thanks for the great presentations. You are amazing scientists. I'm proud to serve as your VC. Good luck to all.
Jen had a question?
There was one more question, I think, from Dr. Grederson. Oh, Jennifer, you go first.
Oh, I just had a silly question. Did you get cold when you were in the chamber?
I was not in the cold chamber, but it was very cold in there because it wasn't very well sealed. So I'm glad I brought sweaters this summer.
Could you go back to the slide of the telescope? It's like, I think it's your second slide. That one there. Tapered capillary optics. This is looks really cool. What is the scale of this, and what's this actually showing, this picture?
So this is kind of just a general setup of the telescope they want to use. I don't think they've gone too far into the whole telescope. At least I didn't work with that part. I was just
Okay.
assigned with testing the detectors that they wanted to use with it.
Fair enough.
But yeah,
Thanks.
sorry.
Are there any other questions today? Well, I would like to thank all of our speakers today, the ones that did internships or REUs, and our 2 graduating capstone students. Thank you for all that you do, and congratulations on a successful job with all of this so far. So let's give them a round of applause. And on behalf of the faculty from Physics and Astronomy, we wish our graduating seniors the best of luck in their future endeavors, whether that be graduate school, industry, or anything that you do. You have shown yourselves to be absolutely out of this world, pun intended. And I wish you the best of luck in your future endeavors. Thank you all for coming today.